So we don't really care about what biochemistry this process describes. It's burning sugar, but the only thing that we need to know is that it can be brought to a form which has only two parameters. This letter A and B, and we are told that these parameters are positive. That helps a little bit in analysis of this system. Now, you might wonder why I'm willing to spend time on a two-dimensional system of equation like this one. Well, I keep telling you that real life is always either many-dimensional or even infinite-dimensional. Because, for me, real life is things like fluids and quantum field theory, which all of them, general relativity, they have very many dimensions. So what happens in these systems, glycolysis is actually a very complicated system with lots of chemicals participating and lots of biological stuff involved, cells and saccharin and God knows what. And what happens to the systems which are barely on the edge of life? So, if they just die out, solution to any of the system is fixed point, and we don't do much more with it, or it's dead. But the systems which are barely surviving off equilibrium with some energy being pumped up, for example, burning sugar that you collect from the plant, and converting it to energy which you need to run the living organism. What happens is that even though there are infinitely many dimensions or tens or hundreds or thousands of chemical processes taking place, most of them happen very quickly or they vanish, they're not sustained by the system. And when you're close to the edge of life, you tend to get in the situation where you're almost dead, but not really. So you have, instead of fixed point one dimension, you have two dimensions. So it's actually not so crazy to look at these low dimensional systems as phenomenologists for highly nonlinear many degrees of systems. Once you're in two dimensions, there are some tricks that work in two dimensions and don't work anyplace else. Strogatz is really nice in emphasizing qualitative aspects of looking at differential equations. In two dimensions, you can draw things in a plane. And in one dimension, we had this trick which said that if velocity is zero, we have equilibrium. That's very important. Now, in two-dimension, velocity being zero means that there is a vector with two components, which is zero. So there are two conditions to get this. But you can ask yourself, what happens if I just decide that one of the velocities, like this one, will be zero, or this one will be zero? The technical word that you might run into for that is nullklines. So just the word that says one of the components of velocity vector is zero. If x dot is zero, that means that we have a relation between x and y, where I can write y as a function of x. It knows this is linear in y. So I put x on this side, so there is an x positive, and then I divide it by this factor a plus x squared. And now that defines a line in this xy plot. And that line starts, if a is non-zero and x is very small, I can forget. So it starts with something whose slope is 1 over a. So it starts out linearly. Now, when x is very large, I can forget a. So this is falling off like 1 over x here. So there is a line, which is this nullkline, where I understand it starts out, it falls off, so it has to have a maximum. And it's something very smooth, so it won't have several, just one. And now, because velocity in horizontal direction is 0, whatever velocity there is, which will depend on x, y according to this formula, it has to point in this direction. Now, if x is very small, then this goes away. And if y is very small, then this goes away. And this is positive, so it means around here the velocity on a null line has only one component close to the origin, and it's positive. So in the y direction, we are moving up. This works until I get up around here. So I keep going this way, and if I now go for very large x, this dominates. So I can forget these two terms. And this velocity now is going down. So there is some point here, velocity changes its direction from going up to down, and it's obviously going to be a point where I go through this maximum of 0. That'll be pretty clear. So that's what we get from null line where a horizontal velocity is 0. So there is a line in a two-dimensional xy plane in which velocity has only one component. It goes up and then it goes down. Now we look at the other null line. We set this guy equal to 0. It looks same as this one, except there is a b up here. And the minus signs work out, so it's a positive b. And then this factor is the same, a plus x squared. So that's a null line in which velocity is purely horizontal. It has no vertical component. When x is 0 at point here, a over b, no, it's a b over a. That's when this is 0. And that curve, when x is large, it's going like b over x squared. So that's falling off faster than this one. So this has to do something like that. It goes down, eventually falls off faster than this thing. And it has a property that velocity, when x is very small, these are positive numbers, so I only have horizontal velocity. So I go this way. I go this way. And now when x is very large, and this velocity has to go that way. So that's what happens in null lines. Now, when both null lines cross, I actually have a equilibrium of the system because both components are 0. So one way to find equilibria, if you don't know where they are, you can just plot these lines for whatever your system is, if it's two-dimensional, and whenever the two lines cross, you have an equilibrium point. These guys only have horizontal component. These guys only have vertical component. When x is very large, this guy is of order, I can neglect this term. When x is very large, so this null line is just b over x squared. If I'm in the region above both null lines, then I'll find that x dot is positive. So up here, I'm moving this y because if I'm at large x and y, I can forget all these terms. So this guy is positive and this guy is negative. So that means my velocity, it's any place here, will point to the right because x component is positive and down. So you can already see that something is going to happen where there'll be a circulation on this graph. So let's investigate this a little bit more. And this can be done in the spirit of Lyapunov functions by defining a trapping region. So remember, Lyapunov function was something that if you have a state space of dimension d, and if there was a codimension one surface, one dimension less. So for example, if you're in a plane, there is a line. If you're in 3 dimension, there is a surface, one dimension less. And if it's a closed surface, like a ball in 3 dimensions, and you can show that velocity every place pierces it and goes inwards, then I'm guaranteed I cannot escape. So that was Lyapunov's ways of finding globally regions in which there must be some attractive objects, which in 2 dimensions are either attractive equilibria or limit cycles. We had one nullcline that looks like that. We had other nullcline that look like that. This nullcline, which is where vertical velocity is 0, and you have only horizontal velocity, that goes up to here. And when these guys cross, there must be an equilibrium. So now, every place above these nullclines, we're kind of moving this way. So that means I'm above. If I go a little horizontal distance, there is a velocity here. And if I look at the particular point, BB, kind of say, I have a very simple formula for velocity there, because stick it in here and it just points this way. It's to be consistent, I should be. So I'm going inside. Here I'm moving this way. On this guy, I'm moving up here and I'm moving down here. And on this one, I'm also moving down, but horizontally, vertically. And now there is a little trick to say it just, specialty of this particular example, not generally true. That if I take a very large x and y, so consider large x and y, and I look at the ratio of y dot this equation divided by x dot this equation. When x and y are large, I can forget these terms. So this is going to minus x squared y divided by x squared y. So it goes to -1. So that says that there is a line of slope 1. When I make x and y larger, it's approximating this. So it's pointing something like that. This line, slope 1 is here. Slope -1, sorry. And that now guarantees that I approach and I look at the remaining terms in this equation, I find out that every place here I'm going inwards. It's a slope which is slightly steeper than 1. Now, I already know that from the left edge, because, I was going horizontally this way, and I'm going that way. I know that anything that starts close to this edge grows upward, and anything that starts close to y equals 0 edge, these terms are not important, has minus x going this way, and y component being b. So it goes up. And now when I go sufficiently far in here, then I can check that this goes inward. So now we have used the null clines to get some kind of backbone. This one is describing that. So what goes in vertical directions? This one is describing that, what goes in horizontal directions. And we have a little bit more information than just where the equilibrium of the system is. We know that there's a general sense of circulation in this flow, and that if we're inside of yellow region, we are trapped. And we also know we have a fixed point, but we don't know about stability of the fixed point. So to summarize where we now are, there's a trapped region, there is a fixed point, there are these vertical velocity, non-zero null-cline, horizontal velocity, non-zero null-cline. And now we do what we always have to do is whenever we have a fixed point, we guarantee that if I start any place in here, I'll fall someplace. But there are two possibilities. I could fall into an attractive fixed point, or I could end up in a limit cycle, and that's the point of this exercise. And the important thing is that in general, having a trapped region is not so simple because you might have any number of fixed point and limit cycles within it, so you have to resolve it. But this flow is so simple in terms of, we understand the polynomials that, lower polynomials that describe it, that's all there is to it. And stability matrix. So the matrix of velocity gradients is obtained by taking differentials with respect of x and y to these two equations. So, from here I get -1 when I take d dx. From here I get 0. From here I get plus 2xy. If I take derivative with respect to y, from here I get a, and from here I get x squared. If I take derivative of y coordinate with respect to x, I get 2x. There's a minus sign. And if I take derivative with respect to y, then I pick up these two terms. This minus sign, so it's a plus x squared. Minus sign overall. I'm working out this example in painful detail because it's a nice example and it's very useful, especially if you're doing biophysics or biochemistry of some kind. Equilibrium, that's where differential equation has 0 velocity in all directions. I evaluate the two conditions at this point. So I have 0 velocity, 0 velocity, equals, then, minus x star plus ay star plus star means the specific value that we have to determine, which is the equilibrium value of x and y. To be still determined. From here we get constant b minus a times y minus x squared. Now, if you just add these two lines, I immediately get that x equals b. Then I substitute that x in either equation, and I get that y star is, this gives me b squared. So I get a from here plus b squared from here, and then there is this b. So equilibrium is very easy to determine. And now I'm supposed to evaluate its stability matrix. In general, it's a function of state space position at equilibrium, and define a new variable, which is the sum of these things. And now I substitute the value of equilibrium point here. So this is a product of these two guys. So it's -1 plus 2 product of these two guys, which is b squared over a plus b. What I call c. This is c, a plus b squared. Down here, I have the same thing I have here with the minus sign, so it's 2b squared over c. And this is minus c. To understand the stability of equilibrium, I have to compute determinant. Now that's simple. I pick up plus c from here, and this part and that part cancel. So I get just c, or writing it out back in the original parameters, I get a plus b squared. So I find out that because both of these things were told were positive parameter, delta is strictly positive. And then I have to compute the trace of stability matrix. So I can, write this as c over c. And then from here, I get c squared. And then this part is 2b squared c. And now, what we know is that when the trace is positive, because this is positive, when it's positive, we are unstable. And when it's negative, we're stable. And, this is slightly tedious because I have to look at when this curve is 0. And, it depends on b to the 4th and b to the square, etc. I suggest you just stick in some program and evaluate. So just looking at a line where this equals 0. And there is a border in it on which the trace equals 0 that divides the stable stuff, and stable stuff is stuff above. And unstable stuff is stuff inside. If this equilibrium point is unstable, it means I'll have to spiral out of it. I even know the direction because we have drawn all these little vectors. So now I have to circulate this way. Now I cannot escape because I'm contained. So the only thing that can happen is I can end up in a limit cycle. So having unstable equilibrium leaves only one possibility, which is a stable cycle. For trace of stability matrix, the equilibrium larger than 0, there'll be a region of AB parameter plane. So what's remarkable about this example, we are getting a great mileage out of almost nothing. I know that I have an unstable point someplace. I know that the stuff that exits from it, its neighborhood, will have to spiral out because it's unstable. I know that if I'm approaching the world from outside, I have to spiral in. And the border between this falling in and escaping unstable equilibrium will be a limit cycle. So that's the power of Poincaré's qualitative thinking about differential equations. Now here we have a very simple differential equation. Now, when you go to biophysical literature, they can get quite complicated, have lots of parameters, but you will repeat the same methodology that we have here. If it's some limiting behavior settles to be just few competing variables, this analysis is extremely powerful and helpful. So I like this. It's a very, very interesting thing. It happens in cardiac dynamics. It happens in neuroscience. It happens in basic energy processes in cells. It's a very common thing and worth our time doing in detail. Now, there is a very general thing to be said about what we have learned in this, so-called Poincaré-Birkhoff theorem. When you have two-dimensional differential equations, what physicists often call flows, inspired by their applications to fluid dynamics, but the notion is much more general. The flow for dynamicists means that if I take a cloud of points and apply to each one my equations and evolve it, the whole cloud will move like a blob of ink in some fluid with a flow. So we call them flows. In two-dimensional flows, meaning smooth differential equations in 2 dimensions, there is almost nothing. There are very few things that can happen. Either you can be stuck at an equilibrium, which could be stable or unstable. Let's say it's unstable. Or you can, in long-term limit, end up on a limit cycle, example that we just worked out. Or you can find out that this limit cycle is not limit cycle, but unstable periodic orbit, which will mean that if you start close to it, you will be pushed away from it because it's unstable and you'll go someplace. And you might go off to infinity. So in chemistry, that's impossible, but in celestial mechanics, it's very typical. You can run away. But one thing you can never do is you can go here and cross that line. That is just not allowed. It's forbidden. And that says that the two-dimensional flows are really boring, because here we are wanting to learn about chaos, but they cannot possibly have chaos. They either die or they, pulsate in some nonlinear way, or they run away. That's all that can happen. Still, stuff is very important, very interesting. So I will persist. And the very important set of applications is now, for me, maybe I'm being prejudiced, most interesting neuroscience, which is that you can look at equation like van der Pol, which is, remember, you start with harmonic oscillator, then you put a friction, but then you put a mechanism to make up for energy loss. This is this nonlinear mechanism here. And that either pumps energy in, depending on how big X is, or it removes energy, depending. And there's some parameters. So that's called van der Pol equation. Very important in making radios before invention of transistors. And one possible situation is that you might have great sensitivity of how you're pumping or putting energy into the system. So you can have a regime where this factor is very far from being 1. So you're extremely sensitive to whether X squared is larger or smaller than 1, because the system behaves dramatically different ways. So that kind of system is strongly nonlinear. And the reason why we care about such systems is they will, as you'll see very quickly, they will have slow build-up. So they'll look almost dead, spend lots of time, getting their energy up, and then they'll go boom, burst. And that's what neurons do. There's a network of neurons, with axons and little roots and connections to other neurons, neuron cells, axons. And what they do is they either do nothing or they discharge the electricity in a big burst. And the stuff that you measure experimentally is actually a bunch of peaks spaced at the time scales which are determined by biochemistry of the cell. So these examples are extremely important because they're every place, this strongly nonlinear limit. And let's massage it a little bit. So we can write this term here and this term, so these first two terms, we can write them as time derivative of first derivative of time here. Here we have x squared, so when we take time derivative, we'll get x squared times x dot. So we get this term, and then there's an extra x term. So let's call this part, give it a name. So this is some kind of cubic, something like some potential, doesn't matter what you call it. And So why are we doing this? We want to give some general, concise notation to the term that dominates when mu is large. And it's convenient now to be able to write, this is written as acceleration, but remember, we like to write things in phase space where you look at velocity and change derivative velocity. So first order equations. Let's write this part all together. Let's call it, omega of x. And now we have an equation. The sum of these terms is 0, sum of these terms is 0. Derivative of this term plus that equals 0. In other words, we have an equation that says omega dot equals minus x. So we can write van der Pol, a great Dutch name, from the pole. And they don't capitalize the various adjectives and definite things. So we have, first equation says that x dot from here equals the sum minus that term, so it's omega minus ufx. And the other equation is so again, where did this come from? It came from this definition. Right? And now it's convenient to move this mu around a little bit. So let's define a new variable called y. So we multiply and divide this by mu, and there is an overall mu y in the first equation. And the second equation, we get an x. And now, why is this convenient? This is the same equation, van der Pol equation, this one. We haven't done anything to it, but now it's designed in such a way that we pull out sensitivity to this parameter mu, because this is small and mu is, and this is large. So, the motion in horizontal direction will be humongous, and there won't be much motion in vertical direction. So what can this thing do? The null lines are very helpful to understand that. You can look on a line when this is 0, so x dot is 0, so mu minus phi x is 0. If I put in my definition of x, it's proportional x and x cubed, so I can write it as x squared over 3 minus 1. So this null line is cubic. That looks like this. So that means that on this line, I can only go vertically to something like that. This is y. And now what happens is if I start any place, suppose I start here, then this is a non-zero term. This is huge. So x velocity is large. And if y is larger than phi over x, this will be positive. So, I'll zoom here at a great speed until I approach the null line. And when I'm on the null line, there'll be a period where they're comparable because I'm supposed to turn around on null line itself. So I have very fast horizontal motion. And now there's a special value here where I zoom away from here very fast. When I get here, I turn around. Now that the velocity y dot is very small because mu is huge. So I creep down until I get to here. Then I go like crazy this way until I get, again, comparable velocity in x and y. When this is sufficiently small, they're of same kind of size. Then I turn around and I do this, boom. So if I start any place in the world, I'll just, from any point like this point here below, I start here, I will land like ton of rocks close to the null line, then I'll creep down the null line until run of it. Then I'll do a very fast jump over here, creep back, and I will get crazy behavior, which is very fast and very slow. So as long as this is not of size 1 over mu, then it's dominated by a large number. So as long as the difference between the distance from the null line is, let's say, of order 1 and not some smaller number, then horizontal velocity is huge. So this is fast. But when I get to this turnover where horizontal, vertical velocity have to be comparable, the y velocity is some finite number, x is just some number here, divided by mu, so it's small. So that's of order 1 over mu, and that's very slow in our limit. So what does that look like in time? So let's just look at the thing I cared about originally, which was x, which was typically some charge in a biological molecule or in a radio tube. So I plot x here, and I look at it in time. If I'm on this thing, I creep very slowly. So I creep very slowly. X is decreasing a little bit, but most of the time nothing happens, so this is long. And then I jump all the way to the far end. I creep very slowly, and then I jump, creep, jump. So this is a clock, but it's a weird clock. The hand of it barely moves, and then it just goes boom, 180 degrees, and then it does it again. And now, this time where you're creeping, the velocity is order 1 over mu. So you have to hang around there for order of time mu. So the larger the mu is, more time is spent here. Now this jump happens at a time, you are flying very fast. So to cross from here to here is of order mu minus 1. And what this physiologically means is you're looking, if it's, let's say, neuronal dynamics, what happens is neuron is some, bag of electrolytes, and you slowly charge it up because stimuli from other neurons come in and increases the charge of your bag of electrolyte until charge is such that you can get through the membrane, and that happens very fast. And once you have discharged, what you do, that means you have sent signal to other neurons. Look, I'm excited. You guys also better get excited. So they pick up the charge on their axons that you have sent out on your neuronal pathways. But you are now exhausted because you have done this, and you have a refractive time. There's some time it takes you to build up the energy again. So this is this short, this long time here. Once you're there, you burst. You can get even more out of this. You can estimate the bursting time, because the time that you discharge is so short, you can assume it's instantaneous because it's 1 over mu, and mu is, let's say, 100 or something, some big number. So you only have to compute the long time. So a period, one time where your system goes around and returns where it started, it's basically sum of how long you hang around here and how long you hang around here in the slow things, so 2 slow times. How long are you staying on null line? And it's 2 because to do the period, you have to hang around on this branch, jump, hang around this branch, jump, so that's this factor of 2. If you're on a null line, then your velocity on the null line you only depend where you're on the null line. It's a function only of x. So change in y is implicit in that. So you have to take derivative of this function. And then you have to take derivative by chain rule of x. Now, this function was a cubic. We define it here. So its first derivative is 3 cancels, and this goes away. So this derivative is x squared minus 1 x dot. But for x dot, you do have a relationship. You can write this also as minus mu x. It's the slow motion formula. And on the right-hand side, you have a formula. This is this guy. So now you have dx over dt. So you can multiply both sides by mu over x. There's an x squared minus 1. This is dx over dt, but we put it on this side. So now we have kind of the equation that on the left-hand side is the thing that we want to do. In other words, we want to integrate this slow time going from this point to that point. And now you have to do a little calculation. That's a problem set, but it's very easy for cubics. This happens at x equals 2, and this happens at x equals 1. So it's an integral of 0, 1, dx, 2, then whatever is here, mu x squared minus 1 dx. You know how to integrate polynomials, and there is integral of 1 minus x. In other words, there'll be part of it, there'll be something that's linear in x, you know how to compute it. So you do this little algebra, there's a mu, and out of linear parts will come number 3 when you evaluate two edges, and out of 1 over x, part of the integration, you get a logarithm, and it turns out to be 2 times minus log. So now you have explicit formulas for the period of this system. So you get quite a bit out of this relaxation oscillator and that class of oscillators. So they're in this level, very simple, and qualitative understanding is very good. And now amazing thing has happened. You did not stop me. I just plowed through all the algebra and I'm done.